Yeah, we use it, but it's interesting for us to know how, like, what it is.
So we have specific heat capacity and latent heat. Both will be dealt with in this chapter. Latent heat. So we will start with specific heat capacity, explaining what that is. So before I start with it, I'm just gonna go into it, explain the introduction problem. That kind of shows why we need the concept of specific heat capacity. So imagine we have a container that is filled with water. So here we have water. So we have 200 grams of water. At temperature T equals 20 degrees Celsius. So, and I will explain very thoroughly during which lessons, when do I need the temperature and when can I use the temperature in Celsius, when can I use the temperature in Kelvin. Sometimes I do it in Celsius, sometimes I have to do it in Kelvin. Yeah.
Is this going to be like chemistry-ish?
No, it's gonna be physics.
Okay, is it MCAT?
Yep.
Okay.
But if you call it physics one, chemistry one more time, I will make the next test so hard.
Only for me.
Cool.
So this is physics. And then we have 200 grams of iron at temperature you can call that T, iron of 100 degrees Celsius. So we have water, and we have 200 grams of water, we have 200 grams of iron, where the iron is 100 degrees Celsius and the water is at 20 degrees Celsius. And then we kind of immerse the iron into the water, and we want to look at what happens to the temperature. And of course, then it has something to say which material we have here. The fact that we have iron and the fact that we have water. So when we talk about specific heat capacity, we're looking for a material constant that changes with what type of material we use. Is it water? Is it alcohol? Is it iron? Is it copper? So in order to solve these problems, we have to look at what type of substance or material used. And that's where specific heat capacity comes into play. And it's correct. It is about the MCAT formula. So I'm going to write down the definition of specific heat capacity, and that definition of specific heat capacity that is the energy required to increase the temperature of how they write it in the book. They write the temperature of a unit mass. That just basically means 1 kilogram of that substance. 1 kilogram of the body by 1 Kelvin. So it's basically where the specific heat capacity tells us how much energy is required to increase the temperature of 1 kilogram of that substance by 1 Kelvin. And here's kind of important feature. It doesn't have to be 1 Kelvin. It could be 1 degree Celsius, because a change in 1 Kelvin, that's the same as a change in 1 degree Celsius. So you could have just said here also 1 degree Celsius. It doesn't matter which unit you use if you're looking for the change in temperature. Then a change in by 1 Kelvin is the same as a change in 1 degree Celsius. And that kind of gives us a formula which we know as the MCAT formula. Because if we want to have the energy required to increase the temperature of a substance of mass m by delta T. We have a formula for that. The energy is then written as Q. The amount of energy is the specific heat capacity. That is the amount of energy required to increase the temperature of 1 kilogram by 1 Kelvin or 1 degree Celsius. So if I take the specific heat capacity and I multiply with mass, and I multiply it with the temperature change, I have the formula telling us how much energy is required. Yeah.
What unit do you use for specific heat capacity?
Yeah, good question. Unit of specific heat capacity. So it's energy per temperature per mass. So the unit of specific heat capacity is joules per kilogram per Kelvin. So if I take the unit of specific heat capacity, multiply with mass, multiply by temperature difference, I get Q in the unit of joules. So this formula, if you understand the definition of specific heat capacity, understanding that's the amount of energy required to increase the temperature by 1 Kelvin, if you have 1 kilogram of that substance, you understand that MCAT formula. You just have to multiply with the mass you have and how much you want to increase or decrease the temperature. So this is a important formula. And the specific heat capacity of, let's say, water that is 4,200 joules per kilogram per Kelvin. And the specific heat capacity for water, no, for iron, is about 440 joules per kilogram per Kelvin. So the water one is not really exact there. It's I think it's 4,180.
80. So we're using chem.
Yeah, it's 83 or 84.
No, I related it differently.
Yeah. So I think it's 4,180. I think I've seen both 83 and 84. Yeah.
So what does it mean? Like, what does that number mean? So that's like, so iron needs less energy to increase the temperature of the unit mass of body by 1 Kelvin.
Yeah.
So it's easier to heat up iron versus to heat up water.
Yeah.
Okay.
And that is actually quite so. Water compared to iron has a pretty high specific heat capacity.
Mm-hmm.
It requires quite a lot of energy to heat water. And that's a kind of important in households and swimming pools. A lot of energy is actually required to heat up water. So during this, when the price of electricity was pretty high, when it passed 4 or 5 kroners for 1 kilowatt hour, one thing the cities did that they just reduced the temperature of the swimming pools by 1 degree. That's going to save quite a lot of money. It has to do with the specific heat capacity of water. It's actually quite high. So we pay quite a lot of money in our household to actually heat water. That's one of the things that we use most electricity to do, heat up water. That has to do with specific heat capacity. So water can actually store quite a lot of energy. So I want to kind of do different examples. We're going to solve this problem eventually. We're just going to do some examples using that formula. Let's call that example 1. Determine the energy required to increase the temperature of 0.2 kilogram of water by 15 degrees Celsius. So let's say we have 0.2 kilogram of water and we want to increase the temperature by 15 degrees Celsius. So how do we use this formula? Pray.
0.2 times the specific heat capacity of water.
Yeah. So C is take the mass of the water, 0.2, multiplied, you can use 4,200 here, and you can multiply by a temperature change of 15 degrees Celsius. So you take 15 here. I have to use my calculator to do that. I don't write the units in the calculations, but this should, oh, all right, I wrote that wrong. That's not C, that's Q. Yeah. So you get 0.2 times 4,200 times 15. you get 12,600 joules. All right, and I'm going to do an example that is pretty similar, but just a different wording of it. So you see, this formula can be used in different scenarios. Let's say I have here a pan, or what is it called?
A bucket? A bowl?
I have to explain it. What is this in
A calorimeter?
a kettle?
A pot.
A pot of water. All right, so a pot of water.
A kettle?
Of water at 100 degrees Celsius. So now we cooked a pot of water. The temperature decreases to 80 degrees Celsius. Let's say we have 1 kilogram of water here. We made spaghetti. 1 liter, 1 kilogram. How much energy is transferred to the surroundings? So during winter time, when the price of electricity is quite high, it's important that when you make spaghetti that you don't pour the boiling water into the sink. You have to pour the water into another container, so that can be a very limited heat supply. So you use the energy, so the hot water can be a limited heat supplies to the room.
Freeze the hot water so you can use it again.
So the thing is, you have here a pot of water at 100 degrees Celsius. The temperature decreases to 80 degrees Celsius. How much energy is transferred to the surroundings? So how would you solve that equation? How solve that problem?
So we can use this formula.
Yeah.
We need to find Q.
Yeah.
We have M, which is 1
Mm.
kgs.
Mm.
We have C, which is just 4,200
Mm.
for water.
Mm.
And then we have the temperature change, which is 20.
Yeah.
And it doesn't really matter if it's negative or positive.
Nope.
It's just a change. And then you just multiply.
So basically understand that we can use the formula to find how much energy must be supplied to the object, or how much energy is actually lost when it cools down.
Yeah.
So here we can take Q, 1 kilogram times 4,200 times the temperature difference of 20 degrees Celsius. And we get 84,000 joules. All right, so that's basically specific heat capacity, understanding the definitions. sometimes they ask for the definitions. You have to you have to write it like this. You have to remember that's a unit mass or 1 kilogram, and it's a temperature change of 1 Kelvin or 1 degree Celsius. And once you understand what specific heat capacity is, the formula should kind of make sense that if you have another mass than 1 kilogram, if you have another temperature difference than 1 Kelvin, you just multiply it by the mass and the temperature difference. Yeah.
Will we ever have to convert to Fahrenheit? Or is that not?
No. In physics, we very seldom use Fahrenheit. We never use Fahrenheit. Sometimes we can use Celsius. And then, or we use Kelvin. Alright, so I think I'm gonna let you work with, yeah.
I have a question. So in chemistry, we had the, approximately the same topic, and the specific heat capacity of water was 4.18. Why isn't it the same?
Like around the same.
No, I think the just book has written it to be in 2 significant numbers.
Oh.
Yeah.
Okay.
No sense. So if you do an experiment, if we did an experiment, I would use 4,184.
No, but the thing that it was like 4.18 joules per kilogram per Kelvin.
Yeah.
Why is it such a big difference in numbers?
Oh no, that has to be kilojoules. It cannot be 4.18. It has to be 4.18 kilojoules per Kelvin.
Divided by Kelvin, right.
Or it was in gram.
It's joules per gram per Kelvin. So it's times by 1,000.
Yeah. So this would be 4.2 joules per gram per kilogram.
That makes sense.
That does not make sense at all. Why do you use grams and not kilograms?
Yeah.
This is how I write it here. Yeah. In per kilogram.
So joules, not kilojoules, but joules per kilogram.
Yeah.
Not kilojoules per kilogram.
No, that would be then it would be a less smaller number. So if it's 4.2, so if it's 4.18,
Yeah.
that either has to be 4.18 kilojoule per kilo. Yeah, it would be 4.18 kilojoule per kilogram, yeah. Or it would be 4.2 joules per gram per Kelvin.
Kilojoules per gram per Kelvin.
Yeah, kilojoules.
No, if you use 4.18,
Yes.
Yeah.
So one of them has to be kilo.
then you have to have joules per gram
Oh, what?
per Kelvin.
That means your mass has to be converted into grams to solve the problem.
Yeah, but also how much energy is required to increase the temperature of 1 gram of the water is 1,000 times less than the amount you need for 1 kilogram. Yeah.
I cooked on the exam. Whatever I did.
Or you have 4.18 kilojoules per kilogram per Kelvin. But use the SI units, joules per kilogram per Kelvin. Then you're safe. Alright, so I'm going to write up some questions you can start with, and then we will soon start with a lab. So we can do questions from the book 8, 9, 10, 13.